Okay, so in the last video, we found out that by trying to solve this problem in the conventional manner using our Euler-Lagrange equations, we had an issue in the end after we differentiated the Lagrangian because we found out that the answer suggested that the angular acceleration was 0, but then the translation acceleration was something like g times sine of beta, which is a constant that depends on the angle. Now clearly that's not correct because according to the no slipping condition, we should have this relation being satisfied, but clearly that is not the case. Unless of course r is 0, but if the radius is 0, then you don't really have a disk rolling at all. So the problem is that there is a basic constraint introduced into the system. So a constraint is something that is going to limit how this thing is moving. And the constraint in this case is this function right here. So at this point, what we need to talk about is something called a holonomic constraint. So holonomic means that we can grab some scalar function. So this is going to be a function of all the possible variables, but notice it's only a function of the displacement variables in the system. And if you can make that equal to 0 in some way, and express it in this form, then that is essentially a holonomic constraint. If the function had other terms like velocities or accelerations, then it would be non-holonomic. So that's an extra degree of complication. But for now, we're just going to focus on this type of constraint. So when we are given this kind of condition, our Euler-Lagrange equation needs to be extended. So we need to basically fix it by adding this term here. So we're going to differentiate the holonomic constraint function with respect to whatever variable we're dealing with here. So we're going to do this for every single variable that we have. So in this case, if we go back here, this is basically the function of constraint. So one way we could write this is, well, f is going to be a function of s and theta. So if we want this to be equal to 0, what we need to do is we subtract this from the other side, so we can say this is s minus r theta. So this is going to be the function. So now if we apply this, what we can do is we can derive the Euler-Lagrange equations using this kind of thing. But that's not going to be all. There's actually going to be a constant attached to this. So there's going to be some constant lambda, which is going to be common. It's going to be the same value for all the different Euler-Lagrange equations we have. So it's kind of the Lagrange, in some way, it is very similar to a Lagrange multiplier. So if you recall from multivariable calculus, when we dealt with Lagrange multipliers used for optimizing functions, we always had some constant that was shared between different equations. So this is the same. This comes from that same concept. We have some constant, and that constant is going to connect the different equations we have to each other. So the idea is we plug everything in, we find what that constant is, and then we can solve for the equations of motion more explicitly. So let's start off with s. So we're going to have Lagrangian with respect to s. And if we look at the equation here, well, the equation is not going to change. This is correct. This is what the Lagrangian is. The only thing that is going to change is the Euler-Lagrange equations we use. So if we differentiate the whole thing with s, this is going to be mg times sine beta. Okay, so that's going to be our partial derivative with respect to s. Now we're going to differentiate the following. So we're going to have the expression L with respect to x s dot. So what is this going to be? Well, the time derivative of the following. We're going to differentiate this, so that becomes ms dot, and then this is equal to ms double dot. Alright, so that's pretty straightforward. Now what do we have here? Well, we need to differentiate this function as well, so we're going to have partial of f with respect to s. That's going to be equal to 1. So now putting all the stuff together, we're going to get ms double dot minus mg sine beta equals to some constant or Lagrange multiplier times 1. So this is going to be the first equation of motion. Now for the second part, we're going to do the same with respect to theta. So Lagrangian with respect to theta, this is going to give us what? Well, there's no dependency of theta, so this is 0. Then we have the d over dt of Lagrangian with respect to the angular velocity of the disk. So we have d over dt of the following. Well, this is the only function of theta dot. So bring the 2 down, this becomes half of mr squared theta dot. Differentiate the whole thing with respect to time, this becomes half of mr squared theta double dot. And now we differentiate our f of s and theta with respect to theta, and that's going to give us minus r. So now the equation of motion for this variable is going to become half of mr squared theta double dot, okay, minus 0, and then on the other side we're going to have the same constant lambda times minus r, so this becomes minus lambda times r. So now we have two equations of motion. Now the next thing we're going to do is we can do a substitution. So basically we can substitute lambda here by this whole expression. So that's going to give us the following. We're going to have half of mr squared theta double dot equals to minus ms double dot minus mg sine beta times the radius r. And now this is going to become half of mr theta double dot equals to mg sine beta minus ms double dot. So the m is going to cancel out. And now this is going to leave us with the following equation. Theta double dot is going to be equal to 2g sine beta over r minus 2s double dot over r. So now if we want to find out what theta double dot is, we can use the following equation that we already derived here. So basically second derivative is going to be to that, so we use another substitution. So this becomes 2g sine beta over r minus 2 times r theta double dot over r. So this one is going to cancel out. Now we move this to the other side, and then our final answer for theta double dot, or the angular acceleration, is going to be 2g over 3r times sine of beta. And now what we can do is we can say, well, we know that s double dot has to be equal to r times this expression here. So basically we're going to multiply this by r, and that gives us 2g over 3 sine beta. And now we can find out what that constraint or what that constant is, lambda, by simply putting this into that equation. So we have ms double dot minus mg sine beta, and you can do the substitution there, and this is going to give you minus 1/3 of mg times sine beta. So this is essentially the value that is going to be related to those two components. Now where do those two forces come in? So we have this force essentially here. So we have this for s and for theta. So what are those actually based on this? Well, it turns out that this particular force here is going to be minus 1/3 mg sine beta. And if we look back at what we got for this, we notice that we got 1. So this just stays as it is. So this is going to be some force. Now the next force is going to be this one. So it's going to be this, and if we look at what we got for this particular one, we got minus r. So we're going to have this times minus r, which becomes positive. So we have 1/3 r mg sine beta. So these two results here, these are the two forces that are constraining the motion of this disk so that it rolls under the condition of no slipping. So if you notice this term here, it is just dependent on the weight. So it seems like this will be related to some sort of normal force acting on it. So basically a normal force acting on the disk from the surface it is rolling on. And this here, we have weight, which is a force times some distance r. So this is actually related to the torque, because we know that we have the distance here, this is r, so this will be related to the torque of it. So both the torque and the normal force that is exerted on it from the surface are going to constrain the motion of the disk in such a way that there will be no slipping happening in this particular scenario. So that's what the whole point of having holonomic constraints is, and essentially deriving the Euler-Lagrange equations using this extra term. This term is going to be the constraint force. So in this case we have two degrees of freedom, so there will be two constraint forces, one constraint force in the translational motion and one constraint in the rotational motion. So that's where this whole idea of holonomic constraints comes in.